Hello everyone. This is the audio visualized recording for the organic chemistry from the book Pardeep. This is from the Pardeep Publications, whose writer is Dr. S.N. Dhawan. My topic is diazonium salts. Introduction. Arin diazonium salts were discovered by the John Peter Greece in 1858. They have the formula AR N2 positive X negative, where AR stands for aryl group and X may be anions such as chlorine, bromine, NO3 negative, HSO4 negative, BF4 negative, etc. Aliphatic diazonium salts are also known as they are highly unstable. They rapidly decompose even at low temperature, forming carbocation and nitrogen gas. Therefore, it is the unit we shall discuss the chemistry and synthesis application of arene diazonium salts only particular with reference of benzo diazonium chloride. Nomenclature. Benzonium salt are named by the addition the suffix diazonium to the name of aromatic compound followed by the name of the anion. For example, benzene diazonium chloride, para-toluene diazonium hydrogen sulfate, para-chlorobenzene diazonium bromide, para-nitrobenzene diazonium fluorobate. Structure of the benzonium chloride. Molecular formula. The molecular formula of benzene diazonium chloride as determined from the analytical data and molecular weight determination is C6H5N2Cl. Grease structure proposed structure for benzene diazonium chloride in which both the nitrogen atoms were directly linked by the benzene nucleus. This structure, however, failed to account the following facts. Its salt-like structure, displacement of both the nitrogen atom by univalent atom or a group is most of the reactions. It reduced the phenethylene diazine in which only one nitrogen is attached to the benzene ring, formation of azo compound by coupling reaction, formation of aromatic diazonium salt from penta substituent anilines. Kikule structure. Kikule proposed structure for benzene diazonium chloride in which only one nitrogen was linked to benzonium nucleus. Evidence in favor. Structure explains most of the drawbacks of grease structure such as its reduction to phenylene hydrazine, formation of azo compound by coupling reaction, preparation of diazonium salt from penta substituted anilines, and displacement of both the nitrogen atoms by the univalent atom or group. Points against Kukul structure. Structure cannot explain a salt-like structure and its instability as compared to azo compounds since both contain nitrogen-nitrogen double bond linkage. Bloomstrand structure. Bloomstrand structure suggested structure for the benzene diazonium chloride in which the nitrogen attached to the benzene ring is pentavalent while the other is trivalent. Evidence in support. It explains all the objective of structure. First and second structure is the further proposed by the following facts. Its ready solubility in which but not common organic solvents is complete ionization as shown by conductivity measurement, the presence of a triple bond as shown by infrared spectroscopy, its instability as compared to azo compounds. It explains the geometrical isomerism as shown by diazostates or diazoates, which are metallic salt of diazonium hydroxide. Preparation of diazonium salts. Aromatic diazonium salts are generally prepared by adding a cool-aqueous solution of sodium nitrate to the solution or suspension of primary aromatic amine in a acid at 273 to 278 Kelvin. Diazonium salts are also found when aromatic primary amines react with nitrite ester such as amyl at nitrite. The nitrite ester needed to propose are prepared by treatment of alcohol and nitrous acid. The process of conversion of primary aromatic amine into diazonium salt is called diazotization. General procedure for diazoization. The primary aromatic amine is dissolved or suspended in a dilute such as HCl, H2SO4, etc. 3 moles of acid are generally used for every mole of amine to be diazotized. 1 mole to form the salt of amine, 1 mole to liberate nitrous acid from sodium nitrite, and 1 mole to keep the reaction mixture acidic enough to suppress the undesirable side reactions such as coupling of the diazonium salt, thus form this free amine. The amine solution is cooled and a cooled aqueous solution of sodium nitrite is added to slowly at such a rate of temperature of the reaction mixture does not rise above 278 Kelvin. The addition of sodium nitrite solution is stopped soon few drops of the reaction mixture produce a blue color with the starch potassium iodide paper showing the presence of unreacted nitrous acid in reaction mixture. Too much excess of nitrous acid is generally avoided since it sequentially in interferes with the reaction of diazonium salt. The excess of nitrous acid may be destroyed by the addition of urea. Since diazonium salts slowly decompose even at low temperature, they are used immediately after preparation. Mechanism. The diazotization of amines is believed to occur by the following mechanism. Evidence in support this mechanism is supported by the observation that aromatic amine containing electron withdrawing groups such as NO2 are less easy to diazotize. This is due to reason that the nucleophilicity of amine group is needed to electron withdrawing effect of NO2 group as such as amine however be diazotized in acetic acid. Conversely, aromatic amines containing electron donating group ortho and para position orthotoluidine and para-anisidine undergo diazotization much more readily than aniline. Stability of diazonium salts. Aromatic diazonium salts are much more stable than aliphatic diazonium salt due to dispersal of positive charge or the benzene ring. Alternatively, the instability of diazonium salt is due to their tendency to eliminate exceptionally stable molecule of nitrogen to form carbocations. Since the phenyl or aryl carbocation is much less stable than alkyl carbocation, therefore aromatic diazonium salt have much lower tendency to eliminate nitrogen than aliphatic diazonium salt. In other words, aromatic diazonium salt are much more stable than aliphatic diazonium salts. Physical properties. A arene diazonium salt are generally colorless crystalline solid, highly soluble in water. Many diazonium salts, especially nitrites, are dangerously explosive in dry state. Therefore, they are never isolated but are usually prepared in situ and used immediately after the preparation. However, certain diazonium salts, such as fluorobates, are relatively insoluble in water and are stable enough to dried and stored. Some diazonium salts also form complexes with metallic salts such as zinc chloride. These complexes are generally insoluble. Arene diazonium chemical properties. Arene diazonium salts are highly reactive compound. Their high reactivity arises due to excellent leaving ability of diazo groups as nitrogen gas N2. They are therefore extremely useful synthetic reagents in organic chemistry. The reaction of diazonium salt are broadly divided into two categories. Reaction in which the diazo groups is replaced by no monovalent atom or groups. Reaction in which the nitrogen atoms reaction in which diazonium is replaced by monovalent atom or group. Some important reaction in this category along with the synthetic applications. Replacement by hydrogen. Deaminization. The replacement of diazograph by hydrogen or the reduction of diazonium salt is usually brought by the treating a diazonium salt with hypophosphorus acid at room temperature, preferably in presence of copper salt as catalyst. These reactions can be carried out by treatment amines with sodium nitrate or hydrophosphorus acid or diazotization reagent. Alternatively, diazo groups may be replaced by hydrogen by heating arene diazonium salt with ethanol. For example, those whole process involving the diazotization of amine followed by reduction of diazonium salt are replaced of the diazo group by hydrogen is called deamination. It may be emphasized here that during the reaction of diazonium salt with ethanol, two products are usually obtained, one involving the replacement of diazo group by hydrogen as we discussed the above and the other of ethoxy group. The relative amount of two products however depend upon the nature of the diazonium compound used, that is group is present. Negative I group is present in the nucleus. Ethanol is used. The replacement of diazoamine by hydrogen predominates. If on the other hand methanol is used, the predominant product is aryl ethyl ether anisole. Mechanism: the reaction occur by free medical mechanism illustrated. Initiation. Next, propagation. Synthetic application. The importance of deamination is illustrated by the following application. First, synthesis of metabromotoluene. Recall, metabromotoluene cannot be prepared by the direct bromonization of toluene and Friedel-Crafts alkylation of bromobenzene due to ortho and para directing nature of a methyl group or bromine group. Second, synthesis of 1,3,4,5 tribromobenzene or SIM or tribromobenzene. Third, synthesis of 3 or 5th dibromotoluene. It may be noted here that it is halogen that is attached to the copper which enter the nucleus. Mechanism of Sandemeyer reaction is believed to occur by a free radical pathway of delented. Gattermann reaction. It is a modification of Sandemeyer reaction in which copper powder and the hydrogen halide are used instead of copper halide dissolved in corresponding hydrogen halide. Yield are often lower, around 40%, than those obtained by Sandemeyer reaction. Replacement by iodine. The replacement of diazo groups by iodine does not require cuprous halide or cuprous at least. It's simply achieved by treatment of diazonium salt with potassium iodide or solution of iodine in potassium iodide. Next, synthesis of para-iodonitrobenzene. Replacement of fluorine. Palt-Schiemann reaction. When an aqueous solution of diazonium salt is treated with fluoroboric acid, diazonium fluoroborate gets precipitated. It is filtered and dried. Unlike other diazonium salt, diazonium fluorobates are fairly stable compound. When dry diazonium fluorobates is heated, it decomposes to Diazonium fluorobates are fairly stable compound. When dry diazonium it decomposes to produce aryl fluoride and bromotrifluoride. For example, mechanism: the reaction occurs by SN1 mechanism. Synthetic application: synthesis of fluorobenzene. Fourth, replacement of cyano group. Synthesis of nitriles. Aryl nitriles can be prepared by heating a diazonium salt with cuprous cyanide or potassium cyanide or copper powder to avoid the loss of cyanide. The diazonium salt solution is first neutralized with sodium carbonate and then treated with cuprous cyanide. This reaction is called modified Sandemeyer reaction. Synthetic application: since hydrolysis of nitrile give carboxylic acid, therefore synthesis of nitrile provide us with an excellent method of preparation of carboxylic acid from nitro compounds. Fifth, replacement by nitro groups. Nitro compounds are generally prepared by treating an arene diazonium fluorobates with an aqueous solution of sodium nitrite in presence of copper powder. Sixth, replacement of arsenic acid ASO3H2 group and BART reaction. Treatment of an arene diazonium salt with sodium arsenite in presence of copper sulfate following by the acidification given as arylzonic acid. Seventh, replacement of aryl group. Gomberg-Bachmann reaction: when an arene diazonium salt is treated with aromatic compound, liquid or its solution as inert solvent of solid, In presence of aqueous alkali, biaryls are formed. Yields are usually less than 40%. Mechanism. This reaction is believed to occur by free radical mechanism. In alkaline medium, diazonium salt are converted into corresponding azo compounds which decompose to produce aryl radical. B. Reaction in nitrogen is retained. Reduction to aryl hydrogen. A, a arene hydrogenium salt upon reduction give good yields of aryl hydrogen. This reaction can be brought about the number of reagents such as stannous chloride, hydrochloric acid, sodium sulfite, sodium hydrosulfite, even electrolytically. If, however, strong reducing agent such as ZnHCl is used, the product is aromatic amine. Mechanism of reduction of diazonium salt with sodium sulfate. The reaction probably occurs through nucleophile attack by the sulfur atom of sulfite ion, both the nitrogen atom forming the dianion of hydrogen sulfonic acid, which is being converted into hydrogen in presence of acid. Coupling reaction. A arene diazonium salt reacts with highly reactive aromatic compounds such as phenol and amines to form highly colored azo compounds. Reaction in which as coupling reaction is extremely used in azo dye industries, whereas coupling with phenols occur in basic medium, that of the amines occur in faintly acidic medium. Coupling action Coupling usually occur as para position with respect to OH or the NH2 group. However, the position of blocked it occur at the ortho position if a compound contain both an amino group as well as hydroxyl group at position with respect to each other. Then the orientation of the coupling reaction can be changed by changing the pH of a medium. The well-known indicator methyl orange, which is widely used in acid-base titration, is obtained by the coupling diazonium salt or sulfane-like acid with nitron methyl aniline. Mechanism of coupling reaction. The coupling reaction between benzene diazonium chloride and phenols or amines is an example of electrophilic substitution reaction in which diazonium ion act as the electro, electrophile while phenol or amine act as the nucleophile. Coupling with phenol. Since benzene diazonium ions are only weakly electrophile, therefore strong nucleophile are needed for the reaction to occur. Further, since phenol is weakly nucleophile but phenoxide ion is strongly nucleophile, therefore coupling reaction of phenols are usually carried out in alkaline medium. Rate of pH. The pH of medium plays an important role in coupling of phenols. As stated below, coupling of phenols is carried out in weakly basic medium. In the alkaline medium, the diazonium salt first forms diazonium hydroxide, which immediately rearrange the hydroxide, which further react with alkali to form the corresponding salt called the diazoate. Since at higher concentration of OH negative, the equilibrium will shift in favor of hydroxium and the diazonium both do not couple. Therefore, it is desired coupling reaction to occur. The pH must be kept as low as possible in the alkaline medium. However, it is too low pH would suppress the dissociation of phenol and phenoxide ion. These four to carry out the coupling reaction, an optimum pH is needed. In actual practice, the optimum pH for success coupling reaction in between 9 or 10. Coupling with the amines, tertiary amines. The mechanism of coupling reaction with diazonium salt or tertiary amine is similar to the phenol, except that the coupling is carried out under weakly acidic condition. Reaction with primary or secondary amine. Coupling of diazonium salt with primary or secondary amine occur in naturally neutral and mildly alkaline medium. Here, NH2 group of the amine first attacks the diazonium cations to form diazonium benzene. However, when the diazonium benzene thus formed is heated in presence of acidic medium, it undergoes diazonium ammonage rearrangement to form para-ammonobenzene by the following mechanism. Role of pH in presence of high concentration of H positive ion. The lone pair of electron on nitrogen atom accept a proton. As a result, the amine exists predominantly in the protonatid. Due to the absence of lone pair of electron nitrogen atom, the amine is no longer nucleophile and hence the coupling reaction will not occur at the concentration of H positive ion. Low pH. Further, as to explained above, two High alkaline, high pH will not favor coupling reaction by forming unreactive diazonium hydroxide and diazone salt in significant amount. Therefore, an optimum pH of 4 to 5 is employed for the such coupling reaction. Thank you.